Good evening, everybody. This is Mr. Molikash again. This is our Week 8 video for Math 172. And this week, you're going to be looking at applications of right triangles. So we're going to look at a couple of examples of that. Mainly, we want to focus on a couple of things. We want to do a discussion of angles of elevation or depression. We want to talk about what that is. We want to kind of clarify this question: where's the shadow? Where's the shadow of a building, right? Have to kind of maybe outline that for you when that comes up in a word problem. And a reminder of sine equals opposite over hypotenuse, cosine's adjacent over hypotenuse, tangents opposite over adjacent. Whenever we're solving problems with right triangles and an angle is involved, you're going to need to make sure that you remember those trig ratios. Another thing I should remind you of is your trigonometry laws and identity sheet that we've been working in. And this next couple of weeks in this unit, you're going to start needing the law of cosines and the law of sines. So I'm going to outline that for you here. This is in section 6.2 of the Julie Miller book, and this is in section 6.3. And whenever you're solving triangles, remember I told you earlier in an earlier video that Mollweed's formula is optional, so you would use that in this unit if you want to check the solutions of a triangle. So what you would do is you'd put all three sides in this side, and you'd put all three angles over here. And if both sides turn out to be equal, then it means you've solved your triangle correctly. And funny thing is that in all of these formulas on this sheet, this is the only one that has all three sides. Sorry, move that up a little bit. All three sides and all three angles in the same equation. So that's what makes Mollweed's formula, kind of significant. But again, you don't need to use it unless you want to use it to check your solution. Okay. So anyway, in future videos, we'll talk more about law of sines and law of cosines. But for now, we want to go through what is an angle of elevation or depression. Okay, so to start with, an angle of elevation is when you start with a horizontal line or line segment, and an angle is formed with another segment that is, if you can kind of imagine another segment lying on top of this one, and we pick up one end of it, and make an angle like this, right? So if the angle is being drawn up from horizontal, then this would make a right triangle, and this would be an angle of elevation. So when questions are asking you about the angle of elevation, then it should be something like this, where it's at the bottom of the triangle, starting from horizontal and going upwards to the hypotenuse. Okay. Similarly, an angle of depression would start from horizontal, and if you can imagine another line segment being kind of on top of that and us pulling it down, maybe like an attic stairway or something, then the triangle would look something like this. So if it's oriented like this, the angle is being drawn starting from the horizontal and then going downward to the hypotenuse, and so this would be called an angle of depression. Okay, so I would take special note of these words in word problems, and if I saw that, I would definitely draw the angle theta, x, alpha, whatever they call it, in these positions, in these pictures, in these diagrams. Okay, so that's what an angle of elevation or depression is. All right, our next question is, where's the shadow? Okay, let's say that you have a problem where there's a building involved, right? There's a really tall building, and hopefully the building is standing straight up. It's not leaning over, falling, or anything like that. And maybe the sun is up here in the sky, way too far away, right? So I'm not a very good artist, but we'll say that's the sun, and this over here is a building, right? So the sun emanates light out of it, and it shines down on this building. And when it does, the ray of light continues on. And so if you can kind of think of, let me draw this in a different color. If you can kind of think of this segment as being the ray of light, okay, then the part of the ground between that ray of light and the building would be in darkness. This is the shadow of the building, right? This is the shadow of the building. And we're hoping again that the building is standing straight up. So, the tip of the shadow of the building would be right here, and then you'd be seeing daylight on the ground or on the grass or whatever on this side of the light beam of light, okay, a ray of light. Okay, so oftentimes you'll see problems that are asking about the angle of elevation of the sun. Well, since the sun is in direct line with this ray of light here, any angle that we find, I'll call it theta, is an angle of elevation. So if it's in line with the top of the building from the edge of the shadow, it's also in line with the sun. So the angle of elevation of the sun would also be the same exact angle of elevation from the tip of the shadow to the top of the building. Okay, so again, don't put the shadow up in the air. The shadow is on the ground. And so many people make mistake by thinking that this is the shadow of the building, when in fact the shadow, the dark part of the where the light is not shining, is this on the ground. Okay, that's where the shadow is. So in problems like this where it says find the angle of elevation of the sun, the shadow of the building is going to be on the ground. The hypotenuse is the ray of light. We don't really care about how long the ray of light is. So what really matters is the length of the shadow and the height of the building. So in cases like this, you'll always use tangent, because tangent is opposite over adjacent. Okay, and speaking of, let's review what this is, right? So the sine of theta would be the opposite side, which is the height of the building, over the ray of light, which again, we have no idea how long this ray of light is, or how long a piece of string would be from the top of the building to the edge of the shadow. That's almost never going to happen. Maybe in a bridge setting where there's a cord or suspension cable or something like that, but not in this scenario. All right, the cosine is adjacent over hypotenuse, right? So that would be the length of the shadow over the length of the ray of light. And again, we have no idea how long that ray of light is, nor do we really care. So usually what would happen is we'd want to use tangent in this scenario, right? So tangent is opposite, which is the length of the building, over adjacent, which is the length of the shadow. So if you know how tall the building is and you know how long the shadow is, you can figure this angle out. Usually what will happen is you'll know what the measure of the angle is. You can use a clinometer or something to figure out how big that angle is when you're standing at the tip of the shadow. And if you know this angle and you know how long the shadow is, you've walked that length on the ground, then you can figure out the height of the building without sending a tape measure all the way to the top of it. You can figure that out just using how far the shadow length is and how big the angle is up to the top of the building at that time. So this would be the kind of thing that you would use to solve that. All right, so okay, very quickly then, we've kind of gone over some applications of right triangles, right? Some vocabulary: angle of elevation, angle of depression, where shadow might be involved with the angle of elevation, and we reviewed the the trig ratios, sine, cosine, and tangent. So what I want to do before leaving you this week is to go through an example problem. And I'm going to, it's really kind of small, so I don't know if you can read this, maybe if you've zoomed out full screen, but I'll read this to you. It says, Roberto has plans to build a tree house in a large oak tree in his backyard. He takes measurements from the ground and uses trigonometry to estimate how tall the tree house can be. Okay, so before I read any more, I know that there's a tree, and we're going to assume that the tree is vertical. And there's measurements from the ground, so this is going to be sort of an angle of elevation deal, right? And there's measurements, there's more than one coming. And we're going to use sine, cosine, and tangent with trigonometry to estimate how tall the tree house can be. And it's not the tree that we're considering here, right? It's the tree house. So pay attention to that key word there. Again, we're not going to care how tall the tree is. All right, so reading on, 20 feet from the base of the tree, so that means Roberto is right here, and we're 20 feet from the base of the tree, which would be right here. So I'll call this point R for Roberto and B for the base of the tree. How's that? Roberto measures 26.6 degree angle of elevation to the proposed bottom of the tree house. So maybe the bottom of the tree house, you know, somewhere up in this tree, and you know, the tree could be like way taller than where we're putting the tree house, right? So there's, you know, there's a tree up here, right? But we want the house to be, you know, a length in the tree, maybe just this length. So this is what we really care about. This is what we want to find the length of. And if we listen to this now again, Roberto measures a 26.6 degree angle of elevation to the proposed bottom of the tree house. So this angle from Roberto to the bottom of the tree house is 26.6 degrees. That's what we just read here. And a 42 degree angle of elevation to the proposed top of the tree house. So here's an angle to the top of the tree house, and this entire angle is 42 degrees. Okay, so what we have is we have two right triangles that are overlapping each other. We have a more shallow angle of 26.6 degrees, and then we have a more steep angle of 42 degrees, right? Now, Roberto is 6 feet tall. Will there be enough room for him to stand inside the treehouse? So, you know, Roberto's measured these angles from the horizontal, from the ground. And it doesn't matter, you know, again, the bottom of the tree could be here and Roberto could be 6 feet tall, and these angles wouldn't change. But what we want to know is this red length bigger than 6? Otherwise, Roberto wouldn't be able to stand inside that treehouse, right? So what we're going to have to do is we're going to have to find two lengths, right? We're going to have to find this length. I'll call that X. And then we're going to have to find the length from the bottom, the base of the tree to the top of the tree house. We're going to call that Y. Okay, so to find X, we're going to use the tangent function. And the tangent of 26.6 degrees, again, this is the smaller of the right triangles, right? So we're using this little 26.6 degree angle right here. Opposite is X and adjacent is 20. Okay, so what that means is that X is 20 times the tangent of 26.6 degrees. And I'll round off a little bit, but I'm going to use my calculator to figure that out. Okay, so that turns out to be 10.015, good enough. And it looks like feet, right? Because this is 20 feet, so these other lengths should be in feet. Okay, so that's what x is, right? So to find out what y is, and I'll do this in a different color so you can see this entire length is y, right? Well, maybe not. I'll just keep it in red, in blue. I'm sorry. I'll do the red later. So now we want to do the tangent of 42 degrees, because now we're looking at this big right triangle, and that's going to be y over 20. Now let's kind of review that, why that's happening, right? The opposite side in this triangle is this entire length from the top of the treehouse to the bottom of the base of the tree, and that's y. So that's opposite, and then adjacent is still 20, but the angle isn't 26.6 degrees anymore, it's 42 degrees. All right, so, sorry, there was something on the paper there. So y is 20 times the tangent of 42 degrees. Okay, so going back to my calculator, I'm going to figure out what that is, and that's 18.008 feet. And the height of the treehouse is the difference in these two things, right? The big length minus the smaller one. So y minus x is this bigger number minus the smaller one, right? And that's 18.008 minus 10.015, which is almost 8 feet. Okay, so yes, Roberto can stand inside the treehouse, or has enough room to stand inside the treehouse. And I'm sorry about my terrible handwriting here, but you get the idea. Kind of running out of space here at the bottom. So, you know, that's just kind of a sample of what you'll see in section 6.1 in the Julie Miller text and in your ALEKS objectives. Okay, so just kind of want to remind everybody before I go to keep using the discussion board. People aren't really using that as much as I'd like for them to, so reach out and ask Mr. Molikash on the discussion board in Blackboard if you're in my class this semester. If not, if you're watching this video and you have questions about this topic, shoot me an email. I work at Johnston Community College in Smithfield, North Carolina, and it's jsmolokach@johnstoncc.edu. Thanks so much.